today we're going to be talking about forces at an angle. Up until now, we've been dealing with forces that are either aligned on the x or the y-axis. So if I have an x-axis, if I have a y-axis, if I have a y-axis on right here, and I have an x-axis here, then we've only been dealing with forces that lie directly on these two axes. So they are all perpendicular. There's always 90-degree angles between these forces. Common examples would be like force of gravity and normal force, friction, and then force applied. That would be one example. What we're going to be talking about today is when these forces are not aligned on the y-axis or the x-axis, so they're not perpendicular. So here's a y-axis, and then here's an x-axis. So when I talk about forces at an angle, they're not aligned on these axes. They're somewhere in this open space up here, right here. So there's an angle here. We'll call that theta, and we say that when we're dealing with forces at an angle, theta is not equal to 90 degrees. So right here, theta is equal to 90 degrees. But here, it's not equal to 90 degrees. So what we have to do is we talk about vectors, and scalars. Vectors and scalars. Now, one unique property of vectors is that they can be broken. They can be broken down. So, for example, say that if I have a park, that's a park, and I want to get and I'm over here in the sandbox. I want to get from the sandbox, and I'm from the sandbox, and then there's a slide. And that's over here. If I want to get from the slide to the sandbox, there are two ways that I can go. I can either go all the way on the x-axis and then go up to the y-axis, so I can go like that. That's version A. Or I could go straight and take another route that cuts diagonal, and I create a triangle. What we've done here is, if we imagine this as a force, if we imagine this as a force, this would be the force in the x direction, and this is the force in the y direction. So let's bring the example over onto the plane here. If we look at a vector, if that's our mass, and that axis, try that again. If we look here and that axis there, that's the y-axis, and then if we do another axis and that's the x, our example would have a force going like this, and we'll call that force applied. We can break up the force applied into a force that goes along the x-axis and along the y-axis. These two things are the same. This method here requires the use of two steps. First, you have to go one here and then two here. But the second method just has only one step. But remember that these two both get us to the same place. So this vector 1 plus vector 2 will give you this vector 3. And so these are equal to each other. What I meant to say was 1 squared plus 2 squared equals 3 squared. That's just coming from Pythagorean's theorem. Let's replace these with some variables here. We'll call that A, B, we'll call this C. So A squared plus B squared equals C squared. So remember that if we are traveling along, we can travel along two paths. So if we look at a problem in which a force is at an angle, for example, a ramp. So if I have a ramp here, and a mass is sitting on top of this ramp, and it's not moving, and it's just in static equilibrium. So that means it's not moving at all. Now, what that means is that if we draw the free body diagram for this, or we have, whoops, let's try this again. Let's put the x and y axes on here. We always want to put the x and y axes, that way we don't get confused. So that would be the y and that would be the x. So let's do the force of gravity first, which we know always exists for masses on the surface of the Earth. So here, that is the force of gravity, which is aligned along the y-axis. It is running right along the y-axis. And then we have something else. Now, if we look here, we have force of gravity. We also know we have normal force, but normal force does not go straight up, directly opposite. Because remember, normal force always acts perpendicular to the surface. If the surface is at an angle, then the normal force must act at an angle. So relative to this, this is 90 degrees. But on the free body diagram, what we see is that it's not aligned to the y-axis like force of gravity is. So now I see that we have a force and an angle, and when we're trying to solve problems, we can't do that. So I will break it up. Now to get from point A here to point B, we can travel along the x-axis some way, and then we could travel along the y-axis, and we get to the same amount. We get to the same location. Remember that from our park example. So we'll call this f of n, and we'll call it sub y. We'll put the unit y, and this will be a force normal, and we'll put the x. Now, here's the interesting thing about this, and this is where the trigonometry comes into play. I'm going to call that angle theta. Now, we know that if we have a triangle, and that's theta, that's A, B, and C, we know that the sine of theta is equal to A over C, and the cosine of theta is equal to B over C. Now, what's interesting is the same principle will apply. Sine of theta, in this case, would be Fny over Fn, and cosine of theta will be Fnx over Fn. So what all I'm doing here is just saying that this is a triangle, and this triangle ABC, this is a triangle. This is a triangle. This is a triangle. So the same properties apply. Now, what's interesting is we can use this to solve for different aspects. We can say that now Fny is equal to, we multiply both sides by Fn, is equal to Fn times the sine of theta. And if we do the same thing here, multiplying by Fn, then we get Fnx is equal to Fn times the cosine of theta. These two formulas are very important when we're trying to solve problems. Now, here's the thing. If we look at, we know that the object is in static equilibrium, so there's actually one more force that is coming into play, and that is the force of friction. Because we know that the object cannot slide, and if we look, we're going to draw a big 0 on this Fn because we don't want to get confused and say because it's been replaced by its components. We know that since the object is not crashing through the floor or accelerating up or down, we know that f of g must equal Fny. That way the f net in the y direction is 0. Now, there's a problem because this force, Fnx, is not being balanced out by anything over here. So what is over here? Well, we remember that there should be some friction involved because that is what's resisting the motion. Now, friction also acts parallel to the surface. So it does not act like this right along the ground. It actually acts parallel to the surface. So friction should act this way. And so we'll do the same thing. This is F of friction. And we will draw the components again. And this time we'll call it F friction Y and F friction X. That's 90 degrees. We'll call this alpha. We'll call it alpha. That's alpha. And then we'll call it, and we'll put a big 0 on that just to make sure we don't get confused. But wait, there's another problem. So now what we see here is we actually see many forces in the y direction. Now, this diagram is getting quite confusing, and it may mislead us. So let's try it again, and this time we'll do it a simpler way. We're going to actually change the x, we're going to try and alter the direction of the x and y coordinates. So we're going to start by drawing the three forces that we already drew last time. This is the normal force. That's the friction force. And this is gravity. Now, if we were to choose to align the x and y axes in the way that we would traditionally do it, we would have a diagram that looks very complicated, like this one. The reason we don't want to do this is because we have many forces to break up, and it may cause us to make mistakes. So we will actually change the direction of the x-axis. We'll actually rotate it about 45 degrees or so, and actually, or however much we need to actually get the two axes to line up with the friction force and the normal force. So we're actually going to change the definition. So now we'll call this the x-axis and this the y-axis. Now we only have one force to break up, and that is the force of gravity. So we can break up force of gravity into force of gravity this is aligned along the y-axis, so we'll call it force of gravity y. This is aligned along the x-axis, so force of gravity x. This is 90 degrees. That is no longer valid, so we'll put a big 0 on it. Now, you may be wondering, well, how do we figure out what that angle is, this angle? Well, to do this, we're going to actually draw a reference line. This is sort of like where reality comes into play. And we're going to draw a horizontal line where the traditional x-axis would be. So I'm just going to rewrite this. If we draw a traditional horizontal line where the traditional x-axis would be, now we look in the top coordinate system trying to find out where our ramp is. So we find that our ramp looks like this, and that is our theta. How does this work? Well, if we look and we envision our ramp again, we see that our ramp looks like this with an angle right here, theta. Now, if we look on this, we can superimpose our ramp on top of this image, and we see that we have theta there. Now, this can be a very confusing concept, trying to reorient the x and y axes. But just imagine trying to align them along these two forces at angles, because we have two of them. Moving on to a simpler example, we're going to look at an example where we only have two forces and one of them's at an angle. For example, say that we have an object that is on a pole. There's the roof there. This is the roof. And the object is hanging on a pole right here. It's a steel pole, so it doesn't swing. And the object is hanging off of it. Draw the force diagram for the object. Well, this is very simple. First, we start off with gravity. We'll draw the forces first, and then we'll write the axes. Force of gravity, and then we'll call this force the force of tension. Now, in this case, unlike this one, where we have two forces that are at an angle, this one only has one. So it's acceptable to keep the x and y coordinates in the traditional manner. So this is x and this is y. And then we can break up force of tension into force tension y and force tension x. That's 90 degrees. That's a big fat 0. And whatever angle they give up here, That's the angle that we'll use down here. If it doesn't make sense to you immediately, don't worry about it. This concept can be very tricky, especially when we talk about breaking up vectors. When we just remember that we can break up vectors into their parallel or x and their perpendicular or y coordinates or counterparts. We can also, if we have a force at an angle, usually on a ramp, we can also we don't have to keep the x and y coordinates in the same way. We can actually change it, and we can reorient the x and y axes. In a later video, we'll do some examples, and it'll hopefully make a little bit more sense. But until then, just remember 3 things. 1, break up the forces. Actually, step 0, we'll call it step 0, draw the diagram. 2, we want to write the equations. We want to try and figure out which forces are balanced and unbalanced, especially when we talk about equations. And then 3, we want to solve. We'll talk more about steps 2 and 3 when we do our problem solving video. Thanks for listening.